Heat transfer is a fundamental concept in physics and engineering and is essential in understanding how many of the devices and systems that we use every day function. It can be defined as the exchange of thermal energy between two or more objects and can occur through three different mechanisms: conduction, convection, and radiation. The system studied in this project is heat transfer involved in cooling of a cast iron skillet containing 1 cup of vegetable oil in it. We've heated up the cast iron and oil to 300 Fahrenheit and have now placed it on a cotton placemat on a wooden table. We're measuring the time it takes to cool down to 110 Fahrenheit, the temperature at which the skillet and oil will not burn human skin.
So here's dot conduction along with the Q dot convection and radiation of both the oil and the cast iron pan, along with the emissivity of oil, which is 0.78, and the pan, which is 0.95, which changes the Q dot radiation of each. Our first form of heat transfer is the conduction within the system. In this case, the heat from the oil is transferred to the cast iron pan, then to the cotton placemat, and finally through the 1-inch thick wooden table. The second form of heat transfer taking place in the system is convection. Since the oil in the pan is a fluid, we could model the heat transfer between the oil in the pan as convection, with the cooler oil being denser and sinking to the bottom and the hotter oil rising. But due to the oil being such a thin layer, there isn't much benefit to doing that. So in this case, the conduction model is sufficient for this. There is convection taking place between the oil and the surrounding air. However, there is a very low output of heat, which is likely due to the walls of the pan protecting the oil from airflow and the surface area of the oil being relatively small in relation to the surface area of the pan. There was a fair amount of heat being put off by the cast iron due to convection, however, not nearly as much heat as the radiation from the oil in the pan, which is our third form of heat transfer. Radiation, transferring heat through electromagnetic waves, ended up being the #1 system of heat loss from both the pan and the oil, which goes to show how important it is to factor into your calculations. It's also important to note that the specific amount of heat transferred and the rate at which it is transferred depends on a variety of factors, like the temperature difference between the oil and the pan, difference in emissivity of the oil in the pan, the thermal conductivity of the materials involved, and the geometry of the system itself.
The first model we will talk about is our SimScape. In this model, we have 3 thermal masses: the vegetable oil, the bottom of the cast iron pan, and the walls of the cast iron pan. We did not include the handle of the pan in the simulation, as there should be a negligible amount of heat loss to conduction into the handle. Now, to go over the paths that heat can take to escape the system, we have radiation and convection off the pan walls, followed by convection and radiation off the surface of the vegetable oil. As stated before, this is where nearly all of the heat loss is from. Now to mention the path of conduction. Conduction takes place from the oil into the pan, and then from the pan into the placemat. Then, in reality, there would be continued conduction into the wooden countertop. However, the counter was not included, seeing as conduction was already the lowest form of heat transfer in the system, and the addition of the counter would have made a rather small difference in results. Our initial Simulink model projected that the pan would cool down to 110 degrees Fahrenheit at about 15 minutes and 20 seconds. However, this initial model was found to contain an overestimation of the surface area of the skillet. Once that was corrected, the simulated model's values were almost identical to that of our experiment. This is our SimScape graph after those corrections have been made. You can see our starting temp still sits at 300 degrees Fahrenheit, and we're projected to hit our target of 110 degrees Fahrenheit at about 33 minutes of sitting at ambient temperature.
Our second model is a SolidWorks flow simulation. Our SolidWorks model consists of a cast iron pan filled with a cup of vegetable oil sitting on a 1/4-inch thick cotton placemat and on a 1-inch thick pine countertop. In the SolidWorks simulation, the oil's heat is being lost through its own convection and radiation, conduction through the pan, then convection and radiation off of it, and finally by convection through the pan and placemat to the countertop. Our simulation calculated that the vegetables oil's temperature would drop to about 110 degrees Fahrenheit at about 34 minutes and 45 seconds. Here's an animation of the heat transfer taking place.
Here is a SolidWorks flow simulation of our model. The arrows represent the airflow around the cast iron pan. You can see that once the air goes inside the pan, it reaches a temperature of about 309 degrees Kelvin or 97 degrees Fahrenheit. As the air flows away from the pan, it cools off to room temperature. You can see that the temperature of the air changing throughout the animation. This is due to the pan and oil losing heat to the air through convection and radiation. In the actual experiment, the ambient temperature or surrounding temperature was initially 72 degrees Fahrenheit, and the starting temperature of the oil was 300 degrees Fahrenheit. Overall, it took about 33 minutes and 30 seconds for the oil to cool down to 110 degrees Fahrenheit, which was likely so long because, as mentioned before, the cotton pad under the pan was a better insulator than initially anticipated. Also, you can see here that the temperature of the cast iron pan was about 10 degrees lower than that of the oil throughout the whole experiment. Here is a video of the end of our experiment. You can see how much lower the temperature has gotten color-wise compared to the start of the experiment, and how hot the pot holder under the pan has become due to all the heat being transferred through it. Here you can see our temperature versus time graph showing the experimental results on how long it took for the oil to cool. As stated before, it took around 33 minutes and 30 seconds to cool to 110 degrees Fahrenheit, which we can see as the two lines intersect.
This graph compares the temperature of oil over time in the experiment, the SimScape model, and the SolidWorks model. The experiment and SimScape model follow roughly the same curve throughout the 35 minutes. The SolidWorks model, however, shows the oil rapidly cooling off in the first 15 minutes and then slowly decreasing the temperature, while the SolidWorks model shows the oil cooling off at quicker rate than the experiment or SimScape. Each plot shows the oil reaching a temperature of 110 Fahrenheit between 33 and 35 minutes.